Hello, I'm Andrew. So in this next presentation, we're going to take a look at the name model structure from a code perspective. We'll take a look at some examples of name input files in the input file format, and we'll have a go at running name off the command line. I should add that the material in these slides refers to earlier versions of NAME, I think specifically version 6.5 that we used for the training course. More recent versions of NAME from version 8 onwards, there's slightly different interface for running them on the command line or through scripts because of the introduction of the MPI functionality, and we're not going to go into that detail in the course of this presentation in much detail. Okay, so here's a look at the contents of this presentation. We'll begin by giving an overview of the model structure. So name is written in Fortran, mostly Fortran 90, but we do use some more modern features from the Fortran language. We'll then take a look at input for name, and in particular, the headed input file format. Then give it an example, take a look at an example of an input file, before going on to look at the basics of compiling and running name, and there the focus will be more on the running of name. I think most users can assume that pre-compiled executable will be available for them to use. The name code is stored under the Met Office Science Repository service, and we have a separate presentation about that later on. But just to give you an overview of the structure at this point. So essentially there are three main folders. There's a folder that contains the main model code. There's a separate folder containing the documentation, and there's a third folder containing various utilities. Looking at the main code itself, most of the Fortran source code for name is contained in the code_name3 folder, although we do have a pre-processing utility that we use on some files that's stored underneath the preprocessor folder. We also have a variety of resources, mainly around reading in of metadata. They're stored under the resources folder. And then we have a folder called RoseStem. RoseStem is a test system that we use in the Met Office, and so that contains a test environment for evaluating name and for testing model changes as we make them. I should also mention we have some supporting code for use of the ECMWF EC codes package for reading GRIB format metadata, and that supporting code is contained underneath the code EC codes folder. Documentation, the source code for that is stored underneath the doc project, but we do have pre-compiled version of the documentation available on the repository in a pre-built version using the link given here. As I mentioned earlier, name is written in Fortran, so it's mostly Fortran 90 or 95, although we have used some features from more recent versions of the Fortran standard as well. We've adopted a modular design so that different components of the model are stored in separate modules. So for example, we have an input module that's responsible for dealing with the input of user information, how that information is processed and then passed to the rest of the model. Or we have a sources module that's used for dealing with source terms and how those are read in and subsequently processed. Name's not really object orientated, although we do refer to it as being object orientated-ish, because there are some ideas from object orientated coding which we are trying to adopt in name. So in particular, we tend to use things like derived types for storing data components together and passing that information around within the model. We do have a viewable version of the code that can be produced with the Fortran HTML converter that is available as part of the software package. Okay, so this next slide gives a broad overview of the workflow within name. So let's start here on the left-hand side, and if I bring the pointer up, there we go. Okay, so name will take some source of metadata as input. So that could be, for example, a single site observation from a weather station. It may be gridded information from an NWP model. And that's stored within a MET module. So the task of the MET module is essentially to store the input metadata. We then have something called a flow module. So the flow module has two tasks really. One is to elaborate on the information in the MET module. So for example, the flow module provides estimates of turbulence characteristics from the available MET information. The flow modules are also responsible for interpolating the MET information to the particle location and to the particle time. And so then that information can be used in a dispersion calculation. At the same time, we need a set of sources and other inputs that are used to populate the model. And then we also require or need to specify what the outputs we want from the model are. And all of this is controlled by these objects called headed input files that I'll come on to next. It's worth pointing out here that each flow module has its own domain of validity. And it's also possible to have multiple nested MET and flow modules. So for instance, we could have high resolution MET data over the United Kingdom region, but that could be embedded within a lower resolution global model, and NAME would automatically select the MET data that was most relevant for its location. So let's look at how we provide input for NAME. And essentially all input that isn't metadata is given either via the command line or via a set of headed input files. And indeed most information is given for the input files. There's very little that's given on the command line. So the input files have a flexible structure. We could give all the input in a single file, but equally we could split the input across multiple files. So this might be useful, for example, where you have a standard set of locations where you may want output and you want to use that for several runs. You can just reference the file. Similarly, if you have a standard set of species or if you have sources, you can just have a separate file to store that information and then call it back in through your main file. The input files aren't quite verbose, but that does tend to make it easier for someone to follow what's contained in them. NAME is usually good at checking the input files and giving you a relevant warning, but there's a couple of gotchas to watch out for generally when putting together input files. One is to avoid tab characters, because tab characters can cause a problem for the processing, and the other one is missing commas, which can cause unexpected errors. So if you see errors that you don't really understand, watch out either for tab characters or for commas that aren't quite aligned properly. So I've introduced the idea of the headed input file, and these are just standard text files, human readable. They can be opened in any standard text editor, and they contain most of the input for the NAME runs using a single flexible format. So the input files contain or consist of a collection of blocks where each block follows a standard format. So here we've got an example setting up the horizontal grids. So we see that each block will have a block keyword associated with it. In this example, horizontal grids. The purpose of the block keyword is to tell NAME what will be defined within that block. So once you've got a block keyword, NAME is then expecting to read a certain collection of data associated with that block. Following the block keyword, you have a series of column keywords. So these are specific to each block, and they give you the names of the variables that are being defined in this block. So in this example, we have the name of the grid, we have the coordinate system that's used, the number of grid points in the X and Y direction, the grid spacing in the X and Y direction, and the reference point X min, Y min for the first point of the grid. So following the column keywords, we then have a set of data values, and these define the actual instances of an object in that block. So in this case, we're defining two objects, hgrid1 and hgrid2, which are two horizontal grids. They both use the lat-long coordinate system, but they have different grid sizes and different grid spacings and origins. So the blocks that we have here will often define objects which are then referred to elsewhere in the input files. So for example, in this case here, we're defining two horizontal grids, the hgrid1 and the hgrid2, which are now abstract objects within name. We're not actually saying how they may be used. So there'll be other references to these objects later on in other blocks that then indicate how they may be used, possibly as the grid for output of a field. We will have a separate presentation later on that goes into much more detail about name outputs. But just to give you a flavour at this point for the types of output name can give you. So output quantities might typically be quantities such as air concentration, deposition rates, dry, wet or total. You can get information about the met and flow, and also diagnostics from the model run, such as the number of particles or the percentage progress through the run. There are typically three styles or formats that we use for the outputs. Fields, which may be 2D or 3D, time series at a single location where you might have the variation, or you will have the variation through time, or trajectories where we follow particular particles and output characteristics along the particle path. NAME also has various averaging and statistical processing capabilities, so you can work out time averages or integrals, or look at exceedance probabilities or percentiles. So this is a good point to take a look at an example of an input file for a relatively simple type of run involving an emission from a single point source. If you follow the link here, it takes you to an example run on the Met Office Science Repository website. And if you join me on the next slide, we can go through the example together. So hopefully you've all managed to open up this example input file, and it's a relatively straightforward example. It's a single point source releasing particles and producing a relatively small amount of output, but it does demonstrate a full working example of an input file. So it contains all the blocks that you need to get NAME to run. So if we scroll down a little bit, you'll see here the basic structure of the file. So it's a sequence of different blocks. So that this is the block keyword here, the main options block. So that tells NAME what is defined in that block. Following the block keyword, you then have the keyword names, the variable names defining what's in that block. And then you have one or more lines to define instances of that block. So for example here, the main options block, you've got a single line, but sometimes you may have multiple lines defining multiple objects in that block. And then we have a blank line at the end, and the blank line is very important because it terminates the block. And once NAME's read the blank line, it's then expecting to read another block. So the blank line is important. So you can see various blocks here defining different aspects of the model setup. So the next thing I wanted to mention was the ordering within the block. So the ordering of the keyword names is not important. They can occur in any order, although obviously the data values underneath must be in the one-to-one correspondence with the keyword names. But the actual order is not important. You'll also see that the keywords are separated, or the entries here are separated by commas. So the separate commas are the keyword delimiters and the data value delimiters. And that means that essentially commas cannot be used in other objects. So you cannot use commas in names, for example. So in this example, you can see that the commas are nicely lined up. And we've padded things with white space, and that's usually a good practice. It means that it's easier to follow, but you don't technically need to have the white space there. You can just have the values squashed up together, but it's much less easy to follow that way. So we would generally recommend having white space lining up the columns. So I mentioned earlier that the format is fairly flexible. You can have everything in one file, or you can split things up into multiple files. And if you do that, you use the input files block here. So the input files give you a list, one or more other files that you read in. So this is basically reading in the contents of this met definition file at this point, and it's as if that file was copied in at that point in the file. So it doesn't matter if the blocks are in this top level file or in subfiles that are referenced through the input files block. While we're mentioning files, you notice here the delimiter characters, the forward slash, the backward slash, they are different between Linux and Windows style operating systems, but Name is clever enough to switch the folder separator between the systems, so you don't need to worry if you're running examples on Windows or on Linux. Name will automatically swap to the correct folder separator. The other thing to mention here is around the format what we use for times. So if you see times in the file, we tend to use the standard format of day, month, year, and then hour, minute, and optionally seconds. On this slide, I want to say a few words about running Name in parallel. So let's go back and look at a little bit of history about Name. So in the early days of Name, all the processing was done in serial. So it was on a single CPU on one compute node that would have done all of the processing work as a serial process. Version 6 of Name, we introduced the ability to run with shared memory parallelism. So that's where you have multiple CPU cores on a single node that share out the work using OpenMP threading. And this is what I'm going to talk about on this slide. Now, more recently from version 8 of the model, we have introduced MPI parallelism, which is a distributed memory parallelism, which is where you essentially have multiple copies of the executable running together, and then the results are brought back at the end and interpreted and output as a single process at the end. But I'm not going to say anything more about the MPI side on this slide. The focus here is on the OpenMP, which is available from version 6 onwards. So for running in parallel, you need to make sure that in your main options block, the random seed has been set to fixed parallel. And then there's an OpenMP options block that is used for setting up the OpenMP options. So here you can have a global flag use OpenMP to indicate whether you want to use the OpenMP functionality. You give the global number of threads that's used as the default for various processes, and then you can override that default for various tasks within Name. The performance speed up you generally get is less than the number of cores that you run on, but the precise nature of it depends on the nature of your run and also on the system architecture. In the next slide, I want to talk about the restart functionality in Name, and in particular on the aspects of the input file setup for restart. So the idea with restart is to give Name the ability to dump the model state at periodic intervals. And the idea behind this is largely if you've got a very long run and you're, perhaps several years of run, and you're 90 or 95% of the way through it, and then suddenly you had a system crash or power failure, it would be rather annoying if you lost all of that work. So the idea with restart is that you can dump out the model state at periodic intervals, and then you're able to restart from the last saved state of the model. So to produce restart files in this way, you need the restart file options block. And this generally contains 4 keywords. So you can run multiple cases in Name, but typically most users would have a single case. And then you specify the time interval between the output dumps. So this is the time interval in terms of Name model time. And then you have settings to whether you want to delete old files as a new restart file is written, or whether you want to write when you suspend the model run. A couple of points to note. You cannot change the input file when you're using restart. There are a few exceptions to that, but generally speaking, you should not change the input file. So it's not really a way of correcting mistakes in your original run. And the other very important point is that restart files can become very large, particularly if you have a large number of model particles that you're tracking. It can quite easily get up into the size of gigabytes. So make sure you write to an appropriate file system that's used for large data volumes. There's much more information on restart in the user guide, including how you actually then invoke a restart from the command line. So I'll say a few words about compiling name, but for most users, they'll be using a precompiled executable, so you don't really need to worry about this. But if there are any users who are potentially developing code and making changes to the Fortran code, they will need to be able to recompile the model in order to run the executable. So there are two, or there's one supported compiler that we have, the Intel Fortran compiler, and we run that both on Linux and with some support also on Microsoft Windows. But NAME has been compiled with many other compilers over the years. So in particular, we've compiled it with the Cray compiler on our own HPC, our own supercomputer. It's been compiled with the GNU compiler under Linux and also the Portland compiler. A long time ago, it was compiled for the Apple Macintosh under Intel. I'm not sure if that would still work, but it has been done in the past. And it's also been compiled on Sun Solaris systems. So in principle, it's possible to compile on Windows, but for most of the users, they would typically be in a Linux environment. So I'll just mention here the two-step process we have for compiling on Linux. So you may recall from the very beginning of this slide, I mentioned about a code preprocessor, and it's necessary to compile that before we compile the main model. So there's a script within the code preprocessor folder called Linux Intel Release that you run to compile the code preprocessor. So that preprocessor is then used by the main compilation to preprocess some of the Fortran files before the main Intel Fortran compilation step can take place. And these days, all of the code compilation is done by running a makefile. And the makefile contains various options for setting up the compilation and for running on different systems. So essentially, it's just a case of running the makefile with the various correct options for your system. I should say there are separate instructions that are available on the Science Repository service for compiling on Jasmine, on the Lotusm Jasmine platform. So finally, we come to how to run name, and that essentially involves how to call the executable file. So there are various ways this can be done. The simplest of which is just to call it from the command line. But if you want to automate the process, then you can add that call into a script. And if you have more elaborate ways of running name, for instance, the operational setup what we have in the Met Office, we have a web interface and a suite behind name that does all of the work of launching it. But essentially, it all comes down to calling the executable with the primary or the main input file as illustrated here. So as I mentioned before, all of the input could be in a single file, or it could be you use a main input file and then you reference other bits of the input from files that are listed within that main input file. It's also worth noting that the name of the executable might be slightly different to the name given here. Again, I should emphasize that the approach given here of just calling the executable with the main input file is only relevant for versions of name before version 8. So at version 8, we had quite a dramatic change in the model, adding in the MPI functionality, and that means we now need to launch the executable through an MPI launcher application such as MPI Run or MPI Exec. So to finish, I'm going to give a quick demo of actually running name. So hopefully you can see my desktop here. And what I have is a copy of the training exercises that you'll see at some point in the next few days. And we're going to try to run one or two of these examples. So, so to begin with, let's just take a quick look. So this is a top level folder, and we have an examples subfolder, so that contains the example input files, and we have an executables Linux subfolder as well here, which contains the executable files. So, so what we have a quick look in there, we can see that we've got several executables. We're going to try and run this one, name3 64bit.exe. So let's just go back to the top level folder and then down to examples. Okay, so if I move now to a terminal window and let's make that a little bit bigger, we can see, so I want to try and run this example here, training example 1. So I'm in that folder and there are the files. And to launch the name executable, we need to go up one level, which in Linux shell scripting is a double dot. And then we do, so that goes up to the parent folder. And then we need to go down to executables Linux. And then it was name3 64bit.exe. So that's what we want to run. And we want to run that on the training example 1. So that's the command we're going to call. Now, before I hit return, I'm just going to mention that this won't work, and it doesn't work for a particular reason, and we'll just see in a moment. Let's hit return now, and it should fail. Yeah, and it fails with a memory fault. That's because the name is quite greedy when it requires stack memory. So there's a command that you need to run when running under Linux, ulimit -s unlimited, and that basically tells the operating system to unlimit the stack size that name can use. We don't see any negative consequences to that. It doesn't seem to affect the operating system at all, but it is necessary in some shape or form on many Linux operating systems. Typically, you might have that at the top of a script that you run rather than typing it in each time. And in fact, when you run this, you just need to do it once in the terminal window at the beginning, and you don't need to do it every time. So it's just a one-time call in the terminal or at the top of your script. So I've done that. I've increased the stack size accessible to name, and now I'm going to repeat the command to try and run the name executable, and this time it should run okay. So hopefully it will run, and it's going to run training example 1. So let's hit return and see what happens. So you see quite a few messages whizzing away, and then a message at the end to say it's completed successfully. So let's just scroll back and see what it actually did. So this exercise is a simple one. It's using single site metadata, and it's just a single source releasing particles. So it does run, it is quite a fast run, as we just saw. So when name runs, you get a header section which gives you various information about the model setup. In this case, we can see the training exercises are currently based on version 6.5 of the model, which is quite old now. And as we go down, you can see there's information about the run start time, the log file for the run. So I didn't mention this, but when you have your main input file, which in this case we called training exercise 1.txt, when name runs, it produces two, or at least two output files, one with a log appendix and the other one with an error appendix, and so the log basically contains a record of everything that gets written to the screen, so it's the log file. If there are any warnings or errors, they get written to the error file, so you can see if it's a problem with your run just by looking at the error file to see if there are any warnings or errors. And we'll take a look at the error in the log file in a few moments. So this is telling you the name of the log file. Potentially you might have restart files as well, so that's giving you a bit of information there about the restart files. You then get a message reading and checking the input files, and hopefully you'll see the message input file successfully read and checked. So at this point, Name's read everything in and it's able to do the run. And so it starts the run. I haven't mentioned cases, but it is possible to have a name run that repeats a scenario, often with different meteorological realizations, so from an NWP ensemble system. But you can also modify some of the dispersion parameters in a run. But most users would only have a single case in the run. And then you should see a message to say updating MET and flow modules at the start of the run. And in this case, the metadata is hourly. Single site MET, so it's reading in from a small file which contains observations from a weather station, parameters such as wind speed, wind direction, cloud cover. That's probably the basic set you need, but then potentially there are other things as well, like temperature and precipitation. So it's read in the metadata, it's processed the MET, it's processed the flow, and then it's able to run up to 1 o'clock. And then when it reaches 1 o'clock, it repeats the cycle. So it reads the metadata into 2 o'clock and processes it, and then it's able to continue up to 2 o'clock. And the run continues in this way. And as we saw, it ran actually very quickly in the case of the single site MET. So it reaches the end, 7, 8, 9, 10, 11. At 12 o'clock it finishes, and then you get the run completed successfully message. And that's what you're looking for, that it's completed successfully. So if we go back now into a graphical view, we can see, I hope you can see the font size here, but training exercise 1, that was the example we ran, and it's produced an error file and the log file. And the log file is just a record of what was written to the screen. So you've got a copy of that. And the error file should be empty in this case, and it is. So there's no errors or warnings, so there's an empty error file. And the output, okay, where is the output going to? In the training example 1 folder, if you scroll down to the output options block, you can see the folder you're specified is ./output/example1. So this is telling Name the folder in which to write the output files. So let's have a look at output example1. There's output, and there's example1. And you can see here the various files that were written as part of this run. And then in principle, so those are all text files from Name. The Name output is all text-based, and then in principle you can generate graphics or you can do other processing on the text files as well. So that was a quick example using single site MET. I'm just going to repeat very quickly essentially the same example, but if we go to example 3, that uses NWP metadata. So the basic run setup is the same. It's a single source for releasing particles, but what we're doing now is using NWP metadata rather than single site MET. And it will run in the same way, but what we'll see is it runs slightly slower. You'll see it taking more time to do each hour of data. In fact, every 3 hours of data for the metadata, because there's more processing to do. So it's having to process a full grid of metadata, but that's still quite quick. It's ran in a few seconds there. So if we scroll back to the beginning, we get the message about the version of Name. We get when the run started, information about restart files, log files, this important message that the input file is successfully read and checked, and then it starts the case. And again, it's running from midnight on the 8th of October 2008. But this time you'll see messages about reading metadata, NWP metadata. And so these are 3 hourly intervals. and then name will interpolate internally to the particle time. So you read up to 3 o'clock, and then it's able to do the dispersion calculation up to 3 o'clock. Then it will load up the next set of metadata at 6 o'clock. So reading in the metadata files for 6 o'clock, and then it's able to do the processing up to 6 o'clock and do the name simulation to 6 o'clock. And so that runs through to 12 o'clock. And again, the run completed successfully message. And similarly, here we've got the output in folder 3, example 3, and you can see similarly a set of output files, the same as before. So that's given you a quick feel for how to run name on the command line. As I said earlier, often if you're doing lots of runs, you would have a script that would set all this up in the script, and the script might also set up folders. It might copy files. It might do some processing at the end, perhaps produce some graphics files, perhaps zip up data at the end or copy it somewhere else. And the name executable would then be called as part of that bigger script. So that's about it for me for this presentation. And when you come to doing the exercises for yourselves later on, you'll see these as 2 examples. But there's other exercises there. They all should run fairly quickly on modern computer systems. They were set up probably the best part of 10 years ago, so they should all run quickly on modern systems. So that's it for me. Enjoy the rest of the course.